Electricity. Isn't it wonderful? It can do mysterious stuff from powering your laptop to your game consoles and even your life sometimes. But have you ever wondered what electricity is? Or how it works? Or even how it is created in the first place? Well, you're in good luck because you're in the right place. In this video I'll explain everything about electricity that you need to know for the exam. It's quite fun when you think about it, and it isn't as hard as you want it to be. The cool thing is to understand it, and so with my expertise and your knowledge, I'm sure we'll whiz through it quite rapidly. So what will be covered during this video? Electrical currents and power, how electricity is generated, including how dynamos and now normal generators work, including transformers. Also, energy and renewability, including the use of power stations to create energy. Different types of renewable energy, for example solar energy. Different types of non-renewable energy like fossil fuels. Comparison of electrical resources. And energy, electricity, and how it is transported across the national grid. And also energy efficiency. I'm also going to cover how energy is transferred, for example chemical energy to kinetic energy. I'm also going to cover energy transformations, and finally heat radiation. So, after keeping your time, why don't we get started? Shall we? So, get ready for the time of your life, a lesson on electricity. Electrical currents and power. Before we get started, remember how electricity works with metals. Metals act as a pathway for electrons to move. Metals have a sea of unallocated electrons that are not used, thus are used in electricity. A power source like a battery gives the force needed to push the electrons. Electrons hit each other, carrying the negative charge, and are not attached to the positive side. A bit like a magnet. So, the key point is, a current is the flow of charge around an electrical circuit. Remember, electrons normally carry charge. There's a reason why it's called electricity. Remember, they're negatively charged. Yeah, back to chemistry, not really. Voltage is the pressure giving the unit or measurement of electrical energy, given or transferred. So, if you're getting a bit confused, think of it like this. Let's say you get a tube of toothpaste. The tube and the flow of the paste is the current, but the pressure given by your hands squishing the paste out is the voltage. A conventional charge, or basically a normal charge, consists of the negatively charged electrons flowing from the negative to the positive side. Remember the signs on a battery, the plus and the negative. There are two types of currents, alternating current and direct current. This is an alternating current. This is typically used in the mains electricity provided you have an electrical subscription. The thing to remember is the electrons in an alternating current go back and forth. It's always like a wave when visually represented on a wave chart. It has a peak voltage. On the other hand, there's direct current. This is mainly used in batteries and only goes in one direction. Unlike back and forth on the alternating current, you can get it from solar energy, which we'll be covering later. On a wave chart, the wave will be straight and will have a steady voltage. So, why does electricity exist, you might say? Well, electrical appliances take in the electrical energy and convert it into other useful and wasteful energies. For example, a TV converts electrical energy into light energy from the LCD or cathode ray tube, produce sound from the speakers, and generate wasteful heat from the components. The unit of power is watts, so the higher watts you have, the more energy will be delivered. A bulb with 20 watts of energy will be less brighter than a bulb with 50 watts of energy heading towards it. Painful, aren't they? Finally, you need to know how to measure certain aspects of electrical power. You can measure some units in a circuit. You can do this by using a certain meter for that. For example, if you want to measure the voltage, you need to use a voltmeter. Same with the amps, an amp meter. You can do this by placing them in the circuit on the whole power input or a certain device in the circuit. But if you're into more mathematical stuff, you need to remember this formula. Remember, P is power, V is voltage, and I is current, as shown in this diagram. Note them down. So you can see, to calculate the power, or in watts, you need to multiply the current, which is in amperes, by voltage, or P equals I times V. So you can see above me, there's also a diagram explaining how to calculate the voltage on a certain item or component inside a circuit. Generating electricity. Electricity has to be made somewhere. Electricity is presently made using fossil fuels, which is a non-renewable energy source. We will run out of it soon. It's typically used in a large productive scale and is used typically in power plants to generate a turbine to create the energy that powers the device you're probably using now. Here are 3 pictures of power plants, natural gas being ignited and coal being grounded up. This process is actually called electromagnetic induction. It's not all complicated as it seems. Break it down. It does involve electricity and it does involve magnetism to create a product of electricity. Generators are usually used in a large scale to produce most of the light energy that you're probably using in your wall outlets and other components that work of the alternating current power. In a short descriptive way, they work by using 2 main components to generate electricity, a coil and a magnet. Other components will be used but will be covered later. Here's a magnet and a coil. So how does a generator work, you might say? Generators work in a weird way, but it's quite easy to understand. First there's a magnet. South, north pole are opposite each other. Now's when the coil gets involved in the process. The coil will be wrapped around the magnet. The more you wrap it in turns, the more energy will be created. The coil will rotate around the magnet, creating a current and a voltage. Thus energy is created. Remember, the energy created will be an alternating current and will be outputted to the 2 ends of the coil. Just a few more things that you need to know before we continue. To increase the voltage and the current of induced electricity or energy is to either increase the strength of the magnet, the area of the coil, the number of turns on the coil against the magnet, and the speed of movement of the magnet. If you turn or move the coil faster, you would also get a higher frequency in addition to the voltage and current. There is also another generator-like power maker called a dynamo. It's similar to the generator, but instead of the coil rotating, the magnet moves whilst the coil stays stationary. I'll be covering this next. Dynamos. They're kind of similar but also different. Dynamos are usually placed on bikes to keep the lights on. They produce a direct current unlike generators. In a bicycle, they work by the wheel turning a magnet inside a coil, creating a current. The energy then gets sent to the lights, converting it into light energy or transferring the light energy, thus how bike lights work. Remember, the energy created will be a direct current and will be outputted to the 2 ends of the coil. Electricity and how it's transported. We got the energy, but now what? Now that we have created energy from the last feature, we are ready to transport it, so let's get cracking. In this part you'll need to learn a few special formulas along with a few rules. It involves Python, by the way. Now that we've got the power out, it has to go now somewhere. It has to go through a few stages before it's sent off. The first stage is called transforming. After the energy has been created from the power station, it is sent to a step-up transformer. The step-up transformer increases the voltage but decreases the current, thus the name step-up. It's the same as step-down. Current goes up, voltage goes down. Simple. So, how does this one work? Here's a shabby diagram of what the transformer looks like. There is 2 coils, the coil being the pink one. The one on the left side is the input energy, so the coil has less turns on the left side compared to the right side, or vice versa. but the other side has more turns, so more voltage, aka stepped up. Easy. The middle thing is the iron core, by the way, just so you know. It is now stepped up to 400,000 volts, but the current has gone down. So what next? Now that it has reached 400,000 volts, it goes through the national grid, aka a group of pylons. You know those metal monsters with cables. They insulate it to prevent any energy loss, and it's called a grid, as a network with spots across the nation create a grid so you can power the nation. So why did they increase the voltage in the first place? Basically, to transport large amounts of energy, you need either a high voltage or a high current. The problem is this, that if you have a high current, a lot of energy will be lost to the heat energy across the network, thus losing loads of energy. It's basically cheaper to step the voltage up and keep the current low. But that still doesn't mean we're safe. Even at high voltages, it isn't really efficient, and it is very dangerous. Back, baby. Let's say the energy has now been transported to my house. I can't use it at 400,000 volts. It's too much. So the solution is, again, to use the transformer, but not to increase the voltage, but to decrease to a suitable voltage for household goods. It may also be stepped down for whatever reason that needs a specific amount of power, but typically 240 volts, which is used across the household appliances. 400,000 volts goes in, 240 volts comes out. Simple. Remember the rule for the step-up transformer. It's exactly the same, but opposite. The power will be stepped down, decreasing the voltage, but increasing the current. Take my charger as an example. Here's my charger. I've taken a photo of the big fat power brick you will also find with the Xbox 360. Inside the box you'll find a transformer. As you can see from the label, the input power is 240-1.6 amperes. Amperes is a measure of currents. And the output is 19 volts and 3.2 amperes. You can see the transformers that are also used. As you can see the difference between them. You can see that 240 volts goes in, but the amperes are 1.6, and the output will be a less voltage but an increased ampere, which is the current. Now the formulas. Yes, we're looking at the boring part, but you need to know this for the exam. You may need to calculate the output voltage from a transformer, so if you know the input and the number of turns on each coil, then you're ready to go. So the formula is primary voltage, or the number of turns on the primary coil, divided by the secondary voltage, or the number of turns on the secondary coil, or if you take the small diagram at the bottom. Just to know, V is voltage, N being the coils on the turn, S being secondary, and P being primary. Energy renewability. What on earth are you talking about? You must be wondering, what powers these machines? To create the power. Sounds confusing, but it really isn't. It's typically known as energy resources. It's the resources that provide energy for certain things we need to power, for example, a turbine. I'll be covering non-renewable energy resources, uses, renewable energy and resources, and finally the contrast between them two. Non-renewable energy resources. We'll need resources to power the turbines in power plants to thus create our electricity. Typically, in present times, we use non-renewable energy resources as it produces more energy than renewable energy resources on the large scale. Non-renewable energy resources include coal, natural gas, oil, and nuclear fuels. Coal, natural gas, and oil are 3 examples of fossil fuels. The thing to remember is, they all run out one day. They do pollute the environment, they damage it, and unfortunately they provide most of the energy today. That's the whole reason we use it presently at the large scale. So what's wrong with them? All the fossil fuels do release CO2. Coal releases the most CO2, followed by oil and then natural gas. This is bad as it does help and add on to the greenhouse effect, which then goes on to create climate change. Burning coal and gas will also release sulfur dioxide, and as you all know, it does create acid rain, which then damages our other living organisms, including those poor plants. Mining causes a mess, as you probably would imagine, and oil spillages do cause a lot of problems to the sea, poor fish. Alternatively, you would think nuclear power would be the best suited, but it does come with its dangers. It costs high, and if radioactive spillages occur, organisms can be affected and may die. So, how do they power our power plants? Unfortunately, most energy comes from non-renewable energy sources. They are used by heating up water to create steam, thus turning a turbine, which turns the coil inside a generator, which again creates electricity. You can see that the result of the generation is energy which gets sent to a transformer and through the pylons, then to your house. Voila! How about renewable energy resources? Presently, there are renewable energy sources, meaning that the resources used in the production of electricity cannot run out, typically expensive and unreliable, probably damaging the environment. Renewable energy resources include hydroelectricity, wave power, tidal power, I won't be covering this, wind power, solar energy, geothermal energy, and finally biomass. Hydroelectricity. Hydroelectricity is a tricky one. It works by storing water in a reservoir. Water is let out through leading to the turbine. It turns the turbine, which turns the coil inside the generator, and you probably know the story from there. The advantages include it's renewable, of course, it uses water, it's very reliable, and you can control the amount of energy required by releasing more water into the turbine or less. It also comes with its disadvantages. It can cause flooding, it can also cause problems for organisms and their habitats, as it may destroy them. The setup price is quite high to get the job started. Wave power. Wave power works by providing air to go through a turbine. It then turns the turbine to turn the coil inside a generator. The air is created by water waves pushing and forcing the air into the turbine. The story continues from there. The advantages include that it's renewable, it uses water and air, and the motion is simple, it goes up and down. Disadvantages include it's very, very unreliable, as waves won't have instantly come. It also is it is only powerful on offshore waves farms, which is a downside as it requires more assembly near offshore premises, meaning more cash. Wind power. Wind power is basically a turbine in the wind. The wind turns the turbine, which turns the coil inside a generator, creating electricity. Its advantages include it's renewable, uses wind, no pollution except manufacturing, and instant power. It's very unreliable as wind gusts don't always occur. They're very noisy and they do spoil the view. Solar panels. Solar panels work by absorbing the solar energy provided by the sun, and it converts it to electrical energy. It can be used in nearly anything, but does produce low energy when compared to other forms of resources. It is best suited in sunny countries, and it works when sunlight is around. Its advantages include it's renewable, uses solar energy, can be used in remote areas. It is also used to power satellites in space. Its disadvantages include it's very unreliable, as it only works when sunlight is available, which most of the time and which most cases is in the daytime, and it produces low amounts of energy. Geothermal energy. Geothermal energy works by drilling a hole into the hot rocks of the earth's juicy bits and pumping water inside. It then outputs steam, which is then used to turn a turbine, which turns the coil inside a generator, thus creating energy. Its advantages include it's renewable. Basically, you won't get ripped off as it is free. Water goes in and steam comes out, and plus it's reliable. Disadvantages include it's very expensive to set up, and it only works some places where hot rocks are close to the surface of the earth. Biomass. Biomass would be a different topic to talk about, but it's really simple. Biomass can basically be animal waste, rubbish, and sometimes plants. It is burnt to create steam that drives the turbine, which then turns the coil inside the generator to create a current. It is also used to produce fuels like biogas and alcohol, for example ethanol. It is usually good as the plants used will have also absorbed CO2, and then the biomass is burnt, releasing the amount of CO2 usually absorbed by the plants early on. There will be no overall difference typically, so it's a win-win for everyone. Resource comparison. Although the renewable and non-renewable resources do include its advantages and disadvantages, renewable energy sources are typically better as they provide better and sustainable energy compared to non-renewable energy. But non-renewable energy is also good as it provides more and more energy compared to non-renewable energy at a larger scale. It is also useful in a large productive scale compared to non-renewable energy. Renewable energy is typically expensive than non-renewable energy sources, which is basically why people or manufacturing goods are used today. Energy efficiency. Save loads of money. You might have heard something called energy efficiency. Basically, it's how well the appliance uses the useful energy. It can give loads of wasteful energy, becoming inefficient, or give small or little amounts of wasteful energy, becoming energy efficient. If you were to insulate or do something to save money, you need to know how to calculate the amount that you have invested. So think about it. There are some examples of measures to be taken to become efficient. For example, I'm going to insulate my house for £200, but the annual saving is £100. I want to save money in the long term, so I have to find out what time I will receive the money I invested in the first place. So I need to divide 200 by 100. Since the unit was annual, it equals 2 years. This is called the payback time. Remember, energy is typically measured in joules or J, or kilojoules or kJ. Also, kilo means 1,000. So 1 kilojoules means 1,000 joules. To find out the power in watts, you need to remember the formula for this. For example, if you have a PS3 using 3,000 joules and you have it on for 20 seconds, the resulting power would be 3,000 divided by 20 equals 150 watts. Easy. Also remember this formula. Power, or in watts, equals energy in joules divided by time in seconds. Or you can use the triangle diagram next to it. You can also calculate the cost of the appliance. Use this formula. Cost equals power times time times cost of 1 kilowatt per hour. This is the cost of how much you're using of electricity, not the cost of the appliance. It was a typo. Energy. There's many types of energy. There's different types, so you need to remember these. Electrical energy inside the current, light energy from the sun or light bulb, sound energy from speakers or cows, kinetic energy, anything that basically moves, nuclear energy from a nuclear reaction, thermal energy, heat energy basically, gravitational potential energy, anything that basically can hit the floor or fall, elastic potential energy, springs, elastics, chemical energy, batteries, foods, cows, potential gravitational and elastic, and also chemical energy are examples of stored energy. Now remember how the energy is converted or transferred. Take a PS3, the electrical energy is converted into heat, and then it is also converted to sound energy. Why the waste? All appliances waste energy. Like a PS3 takes in the electrical energy and outputs sound, heat, kinetic, light energy, and also electrical energy, as well as processing. The sound and heat are wasted as they are not useful. The sound is generated from the fans, and the heat also is generated from the processors or chips inside the components. They are also useless. Light, kinetic, and electrical energy is useful as they are mainly used, unlike the useless products. I want to calculate the efficiency of my PS3, so I use this formula. Efficiency equals useful energy in divided by the total energy out, and multiply that by 100. So if I had my PS3, the energy would be 3,000 volt, 3,000 joules of energy outputting. But the useful out of all the 4,000 joules, I would have to divide 3,000, which is the useful energy, divided by 4,000, which is the overall energy, multiply it by 100, giving 75%, which is my efficiency on my PS3. Finally, heat radiation. Thermal radiation involves the emission of electromagnetic waves. All objects are absorbing or reflecting heat. You can feel the heat radiating if you go near somewhere, something hot, and you feel the heat. Scary, ain't it? Remember, dark might absorb heat better than glossy surfaces. They also reflect heat better than the glossy surfaces. Silver surfaces reflect nearly all the heat radiation, whether it be infrared or something else. Black surfaces, on the other hand, absorb heat, meaning the heat can get in both ways. Good for ventilation in engines too. Before I end the video, I would like to show you a demonstration of solar energy being transferred to different multiple examples of energy, including kinetic, light and sound energy. As you can see, there is a solar panel in front of me I am holding right now. I'm using the solar panel and I'm using this light as a light source. I'm going to use it to power up the solar panel so I can get the energy transferred to my sources, including the ones that are kinetic, sound and light energy broadcasting. As you can see, I've got the fan with me, which will be providing a kinetic energy transferation. As you can see, I will be plugging the red power cord into the red socket and the black power cord into the black socket. And as you can see, I am now plugging it in. I'm soon going to get the solar panel and make it come closer to the light. The light will act as the sun or any solar energy that is heading towards it. So as you can see, when I point it there, the fan starts moving. The energy produced is sound energy, kinetic energy and heat energy from the motor. It's a really good exercise and it will be teaching us a lot of features. My next feature is also the use of solar energy on sound. I've got the buzzer. Sorry, but there's no sound in this video, so I can't really explain or show you what the sound will be coming out, but I can reassure you that any sound will be coming out here. As you can see, I'm plugging the cables in, the positive and the negative side. Remember, this is providing a direct current, not an alternating current. So here I am showing off the parts. So I get the solar panel in my hand and I place it towards the lights. You can't hear this, but there is sound coming out. I can reassure you there's sound coming out. It's an example of sound energy coming from solar energy. So basically, solar energy converting into sound. Here I've got a light box. I'm going to plug in the negative and the positive cables inside, like I've done previously. This one is something visually. From what I expect, light energy goes in, or solar energy goes in, and light energy comes out. As you can see, the light turns brighter as I make it come closer to the light, and it gets less brighter once I move it away. It's very good, and it shows me the many possibilities that renewable energy sources can provide for us. Thank you for watching my video.